Ahoj, dobry den. I'm Adam. Thank you for coming for my talk. I know it's been a long day. Today we are going to talk about knocking at the door of PostgreSQL. You can notice I stroking out PgBouncer in the talk. If you came for that part, sorry, but don't worry, it will still apply and we will discuss it. So first off, what will you get out of this talk? First thing is fuzzing for you. Is this something that you should be doing, that is fun for you? If you don't know anything about fuzzing, this is the good talk for you. If you know a lot, I think you can still take some things out of this. You will learn how to start, and most importantly, you will learn how to approach complex software like PostgreSQL, which is really not intuitive to approach with a fuzzer. So who I am a principal program manager at Microsoft on the PostgreSQL team. I'm an OpenBSD committer, but I'm slacking for a while now. I also have background in info security and systems programming. And I have this internal belief that operating systems, databases, and browsers are essentially the same thing. They are just different flavors. I actually worked on all three. I did commit to Otter browser, which is an open source web browser. And I actually ported Dartium, which is a fork of Chromium, onto the BSDs. And that was the first time I looked under the hood of Chrome and got really scared. So the agenda for today is, what is fuzzing? We will go through a toy example of it. We will talk about why fuzz PostgreSQL, why it's a worthwhile endeavor to do. What are some good fuzzing targets, because PostgreSQL is large. How to fuzz networking, and conclusions. So fuzzing is an old concept. It's actually around since the 1988. And what it is in a black box testing fashion is essentially throwing random inputs at a computer program and seeing if it crashes or not. So if you look at the slide, like the caveman here tries to throw different things, but really some things work, something doesn't. There's no analysis in trying to optimize the things that we throw at it. Later on, the concept of gray box testing happened, which is what if we try to be a little bit smarter about what we test. So if we are, for example, testing SQL statements on a database system, maybe we figure out that there's no point constantly throwing invalid SQL statements because we will not trigger some interesting behaviors, like, for example, indexes being used, because we never get to actual query execution. And we can spend a lot of compute time generating random inputs and only exercise the initial part of the parser, never getting further into the engine. So we can start mutating the inputs with some rules. We can employ genetic algorithms to it. And also, most recently, the concept of instrumental fuzzing introduced a feedback loop into the process, which is the moment where we not only look at did it crash or not, but what's internally happening with what we are testing, right? So fuzzing is detecting the unexpected inputs. Like, you're trying to figure out what you can throw at the system to get as deep as possible. You want to trigger crashes, hangs, memory bugs. You can use the coverage feedback from what code paths were hit. It's great at finding weird, deep, non-obvious bugs. So weird interactions that are very hard to predict. And some of the great targets for that are parsers, protocols, and any security critical code. Essentially, any form of external, untrusted input that's being processed by your system is a great target for fuzzing. So let us look at a sample toy program I'm taking a look if it's big enough. It seems so. So on the left is a very simple C program. It has a hard-coded sequence of if statements that check if the first like it reads a 32 character length buffer from standard input, then checks if the first 4 of them are the word fuzz, the letters that will together form the word fuzz, and then it looks if anywhere in the string there is the word crash. If all of that is happening, like if that's contained within the input string, we will do an illegal operation and essentially crash our program. This is deliberate, but you can imagine some form of a complex software that has this crash hidden. On the right-hand side of the screen, you can see the flow graph of this program. And you can see the 6 branches of conditionals represented here. We only have 2 if statements, the 3 if statements in the code, but we are actually looking at all branches of the code. So each check using the short circuits of C is represented in the flow graph here. So if you would walk through this program with some sample input, a fuzzer could start with an empty string and would fail on the first check. But what modern fuzzers do is you're not running a binary of your application. You're first compiling your application with a compiler that's tuned for your specific fuzzer. So for example, if you're using AFL, it has its own compiler variant, and what it will do is for every branch of the code that you see here, it will add a little call that will log if this branch has executed or not. So what would happen here is it would fail to find a bug, like the program would execute successfully without errors, but it would note, okay, for this empty input, I hit this one branch. And it will try to apply some form of mutation on the empty input. In this case, there's not much you can do on an empty input except for growing it. So it would randomly grow the string. You could also speed up the process a bit by giving it some better seed. So if you imagine that you're testing a very complex file format like XML or JSON, you can provide it a seed of a properly formed file to get further faster, but it's not required. So if we would switch to an input that's the string test, we would get a bit further and bail out on the second statement. And again, this would be noted. So modifications would be applied to the string that the fuzzer noticed we passed the first 2 checks, so it would leave the first character potentially unchanged in some iterations, knowing that it's probably the significant bit of information in the input. We got further in the binary. So it would start modifying the other parts of the input string and maybe growing it further. So as we do this operation, we would get farther and further into the execution until we pass the first if statement. And finally, we trigger a string that's triggering the crash. But this might not look like something we would do, right? If I would read the code, I would just write fast crash without like the gibberish in between. But this is an actual input that a fuzzer found on this specific toy example. So running things under a fuzzer looks like this. This is AFL, American Fuzzy Loop. So AFL was developed by a Polish security researcher, Michał Zalewski, also known as El Kamtów, who worked at Google at the time. And he really popularized the instrumented feedback fuzzing. AFL is essentially a security-focused fuzzer. It's very fast. It employs compile time instrumentation and genetic algorithms to automatically discover clean, interesting test cases that trigger new internal states in the binary. So this is actually running the toy example. Another example, it's pretty small on the screen, but how it looks is not really important. The most important usually is how many executions per second it does. This is HongFuzz. This is a general purpose fuzzer that uses code coverage, software and hardware based, to find bugs. It's multi-process, multi-threaded, and supports persistent fuzzing for extreme speed. I can talk a bit about that. So in the past, AFL was single-threaded. There is a new version of AFL called AFL++, and also a new library called libpq. And both of them now support persistent mode. In the past, the way fuzzers worked is they expected a binary, and then they executed that binary and provided a random input somewhere, most notably on the standard input of the program or as an execution parameter as a command line argument. So that, you can imagine, is pretty slow because for every test you want to do, you have to fork, spawn a new operating system process, observe it dies or not. So what can be done nowadays is you can export a symbol in your binary. Think of it as an alternative main to your application code that the fuzzer compiler understands and is able to invoke instead of the main of your program. And you can treat it as like an input to a unit testing framework. It would essentially run this without spawning new forks of your process, executing it in batches of thousands, for example, much faster than it could with spawning binaries. And this is actually the most important thing with fuzzing, because a lot of it is instrumentation based from observing executions and randomization. So the fastest you can iterate, the further you will get with your data. If we look at a sample example of a report generated by HongFuzz on the test toy example, a lot of this is not important right now except for the fuzz name, which is just like a file placed on disk by the fuzzer, which is, hey, I used this input to obtain the crash that you are looking at right now. And if we go to the terminal and invoke the toy example, passing in that exact file from disk to the toy example, it will segfault the binary because it triggers the crash. And I run cat on the file, so this is the fuzz CR crash input that the fuzzer itself found. Now this is a toy example. AFL actually found very interesting bugs in the wild. So this is a blog post by Michał Zalewski on pulling JPEGs out of thin air. So if you're fuzzing library for JPEG files, you can give it a JPEG as a start, but Michał decided here to give it nothing. And within 6 hours on an 8-core system, it got its first blank grayscale image, which is a 3 pixels wide and 784 pixels tall grayscale image. But then the moment it found that file, it started mutating that image, rapidly producing a wide array of new pictures of, for every execution, which are represented by other squares on this screenshot. So why fuzz software? So we can think of testing itself as a polite form of interacting with your program, right? If you're a programmer or if you're building systems, you're doing unit tests, and what you're testing is the known agreed upon interface of the happy path, what you expect the code to do, the edge cases that you can think about, what can be done, but it's very polite along the edges of what's expected. What fuzzing is very root. It goes in by the windows anywhere it can. It won't look at what you expect can execute. It will look at what code paths it can trigger by feeding random things into your binary. So when you do that, assumptions break. And when assumptions break, bugs appear. And this is the wrong slide. I wanted to use this one. So fuzzing is actually used in the wild. So Google runs a massive continuous fuzzing cluster, OSS fuzz. They run it against SQLite, for example, and they run OSS fuzz, libpqr, AFL, and a bunch of other things. SQLite actually has a full documentation page on how they integrate various forms of fuzzing in their continuous improvement process, and I think that PostgreSQL should be doing something similar. And one of the first bugs that AFL found was a pre-authentication issue in MySQL itself. It was an integer overflow in the auth packet where you were providing your password. So it was a DOS type operation. So if we look at PostgreSQL itself, it's huge scope. There are a lot of areas that are interesting targets for fuzzing itself. The most obvious one is the parsing. Sorry, I'm trying to adjust this. So the most obvious one is SQL parsing and anything to do with SQL statements. And the reason for that is there's a lot of mature tooling that generate proper, validly formed SQL statements, and it's very easy to write tests. You just connect to a running PostgreSQL instance and throw SQL statements at it and see if it works or crashes or does whatever you expect. Like the most popular one is SQLsmith. And at this point, I think the parser is a very well-tested piece of code. It's not only used in PostgreSQL, it's been ripped out into multiple places and used by separate tooling. So I think there are other more high-interest areas like extensions, anything to do with extensions in PostgreSQL, since they can do anything with the whole process. The scope of changes that every extension introduces can be unpredictable and a very nice target for fuzzing. That includes both integrated extensions like PageInspect, HStore, pgcrypto, and external ones, especially those that do foreign data wrapping. I also think that the replication protocol can be a good target. You have logical decoding, setting up the streams, replicating to a hot standby. Those are all very complex processes. Anything to do with parsing the file format, the on disk. So storage, like heap page reading, tuple decoding, access methods, anything that's to do with files, but also utility and DDL paths, like altering tables, creating braindexing and partitioning logic. Personally, I think the most interesting target is client and protocol handling, and most importantly because it happens outside, it's externally available. So if there are issues there, they are much more risky than a bug in the replication protocol, which already requires some form of authentication. So in my testing, I focused on libpq. And interestingly, I'm not the first person who decided to fuzz PostgreSQL. So I found this accidentally after I've done my testing. I accidentally stumbled upon the same presentation on two conferences, unfortunately in Russian, which I don't know, but I watched them with automated translation and trying to figure out how much I can understand from it. And they did the same thing, selecting the same targets but with different methodology. And I think it's interesting to cover the different approaches. The person doing the testing, I believe, is Nikolai Shaplov. I hope that I pronounced this correctly. And the second work I found, and nice to note is that they actually found and reported 3 bugs to the PostgreSQL mailing list with this. I don't know if there are other bugs that they found and didn't report. Another interesting paper I found is the Squirrel testing database management systems with language validity and coverage feedback. This is actually a tooling that's focused on fuzzing databases, but mostly focusing on the SQL execution, so generating proper SQL that can trigger bugs in databases. They run the longest time on MySQL and 11 days against PG and, they run the longest time against SQLite, then 11 days against both PG and MySQL. They found 63 bugs in total. 51 of them were in SQLite, 7 in MySQL, 5 in MariaDB, and none in PostgreSQL, which reinforces my idea that the parser and SQL handling in PostgreSQL itself are pretty mature. So probably there are other areas that are more worth targeting. So what are the challenges in fuzzing something like PostgreSQL? There are 3 main areas. One, PostgreSQL is a process per connection, and fuzzers can't really work with something that forks into another process. So there are 2 approaches that you can do here. The one that I took is writing a separate harness that essentially links the parts of PostgreSQL codebase that you want to test. The downside to that is you have to write code, maybe export symbols from PostgreSQL, and do a lot of setups for memory handling and signal handling, like pgtry, trapping exits, and things like that. And it becomes challenging to discern between PostgreSQL crashed versus it thinks I'm feeding it something that is invalid and it crashes on purpose. So we have to write additional code to discover that. And anytime you change your fuzzing target, like I did in my example, you have to redo the harness, rethink what you're doing. So it's a long and time-consuming process. The approach from Nikolai's talk is to disable fork and exec in PostgreSQL itself. So in the code place where they run exec and spawn, they fake that the pit of the process is the child process, and they prevent PostgreSQL from forking on a connection. The second problem is TCP/IP overhead. So again, PostgreSQL expects to get data from networking. I was thinking about single user mode, but it disables networking itself, so that's out of the question. Having an external harness, I don't need networking. I can just feed data directly into the parts of libpq that parse whatever would come over the network. So I started with pq get message, but it became very narrow scope quickly. So I expanded and targeted the startup packet itself, which is a larger piece of the networking, but required more setup to start testing. In the other team's approach, they essentially stopped out the whole networking layer. So they intercepted accept, select, bind, and other networking calls. That gives them more flexibility in what they want to do. So they would plug in the fuzzers into their fake networking protocols, so they can introduce things like random latencies or feed into normal connections at random places the output of a fuzzer. The third problem is persistent storage. So if you're testing against running PostgreSQL, between executions, on-disk data will change and shared memory will change. So that would cause you to have different results that are unrelated with your current run. So you will get issues that are very hard to reproduce. So in my case, that problem goes away because I'm actually not running PostgreSQL. I'm targeting in this case, the networking layer. That problem would still exist if I wanted to test something related to file formats or something that would result in changes to disk. In the case of the other team, they decided to use Btrfs and snapshotting and essentially roll back the file system snapshot between each execution of the test. So if I had to say what's the better approach, I think there's no better approach. For sure, they have much more flexibility in what they do. But on the other hand, it's a more complex test because it tests all components at once. You cannot narrowly target. And things like rolling back a file system between each execution, even though snapshots are fairly instant, that's still not the same as running a function thousands of times within memory. What I think would be the best approach is to have designed and externalized fuzzing targets in PostgreSQL itself. So when you know you have a piece of PostgreSQL that's critical, we could define an interface that expects random data, and the signature of an entry point for a fuzzer is data and length. And you can use that to test any subsystem you're developing. And in that way, we could automate fuzzing into release cycles in a way that's more structured without building external harnesses all the times. So just for including this is my test of PostgreSQL running in AFL. This one is super slow because I actually ran it with full code coverage. So I wanted to generate like human readable code coverage that I will show on the next screen for several reasons. I wanted to physically see like, is it working and am I even getting further into the code base, or am I thinking that I'm testing and I'm stuck? And here's the same thing running with HonkFuzz. I know it's big, I'm going to zoom in just on the code coverage for a second. So if you look at the code coverage, so I think this is from where I was running with pq get message, so the very short narrow scope. You can see next to this if statement, there are 3 pluses, 1 minus. And what this represents is there are 4 ways this if can be evaluated, because there's like the first length check, the second length check, there's an or in between, and there's an else implicit branch, right? So the code coverage tells me we covered 3 of the 4, 1 is uncovered. And you can see that further, we have the next if statement that's never hit. And why this was never hit is in my harness, I made a mistake. And my mistake was that I ended up calling pq get message with the length 0 hard-coded. And that essentially meant like it never will go past this. So it's very easy when you're writing your own harnesses, if you make a mistake in how you generate the input data, you can be stuck in the code base, and I could have left it running for a week, go back after a week, it would do millions of executions, but would find nothing because it's mutating data, but I had a hard-coded block essentially that made it stuck in one piece of the code. So you have to be very careful to make sure that all the variable inputs are controlled by the fuzzer, and directly or indirectly when you are doing this. So I didn't get very big bugs or crashes with PostgreSQL. There are several reasons for that. One of them is PostgreSQL is a very defensive code base. So some of the problems I had for a long time was I hit crashes, and those crashes, after I investigated them, happened to be PostgreSQL essentially doing the exit in a way that invoked signal handlers, and it looked like a crash, so I had to investigate that. Second, I was running on a local laptop, so the number of executions were not pretty big, and with code coverage enabled. So if I'm built a debug build with all the code coverage and also generated the files needed for that, that slowed down the number of executions extremely that I could do. So some of the next steps that I would like to do with this is, one, test on bigger hardware, essentially run this for a longer time and see where it gets. And the second thing is evaluating that option of actually adding entry points, like good entry points for fuzzers in PostgreSQL proper itself. We can swap to the code because I see that we have still some time. So let me see if I can bring this up on the screen, but that might be troublesome. Give me a second. I need to just change the display settings to mirror the screens. Now you see my presentation mode. And we can go to the harness. So essentially, what happens is there's this fuzz1 input, which is the persistent mode that allows AFL or hung fuzz to execute in a loop all your code. And after that, you have all the setup. Let me find the specific entry points. Fuzz1 inputs. Okay, some of the problems with Postgres is actually also long jumps. So that was a challenging thing to solve. Some of the exits happened with set long jump within PostgreSQL, and that can really mess up execution and makes debugging harder. You have to set up memory handling, pgtry, pgcache, and also discern between this is a panic from within PostgreSQL that's proper versus this is the application actually crashing. There are memory contexts that you have to create. I'm actually building a startup packet. So the data and size comes from the fuzzer. And the build startup packet function takes, I can actually jump to it, I think. Build startup packet. So it takes the fuzz data and extracts, applies the random bits in the fuzz data into formats that represents how a startup packet would look. I could just push all of this, add one function, but having a proper format allows me to move further faster. And some of the initial bugs I had was essentially building this packet improperly, making hard-coded decisions and not moving forward. So when we have this startup packet ready, we set up a socket, and then we call fast process startup packet, and that's the only change I did to PostgreSQL itself. That was not here. Just a second. Okay. Backup startup, yes. Okay, I'm not going to search for it now, but essentially what this does is, this is an external symbol I added in PostgreSQL because process startup packet is a static local function within PostgreSQL, so it's not exported otherwise. And I didn't want to externalize a function, so I wrote a simple wrapper that, hey, this is external, you can call it. And that's the only change in PostgreSQL itself. And in addition, there are signal handlers that are implemented here. So for sigturn, sigquit, sigalarm, essentially to figure out, to wrap proc exit, to figure out if PostgreSQL crashed or did we crash. Okay. So let me switch back to this. And can I disable the presenter mode? Okay, I think it worked. So essentially, okay, this works. So this is essentially what I have prepared. Wanting to use some of the remaining time, I wanted to mention that there is a new iteration of the POSET conference coming, which is an online, fully online conference that we organize. The call for papers is still open, but consider it the last call because it closes very, very soon. So I'm going to leave this up in case you want to scan this, and if there are any questions, I'm very happy to take them. Yeah? Yes, but maybe for...
So I'm wondering, because I don't know if you mentioned it in the beginning, but at the end you said that you want entry points for the PG development. So what is the current state of it? Is there any fast testing happening already, or how do you envision this basically? Because I don't know what type of tests they are running for the project.
So I don't think there are any existing ones defined. I didn't find any. What that would require is figuring out good places to test. Like I think like the startup packet is a nice place to test. There are some other in networking at least that can be considered. We talked about the scope previously, but then so for example in the Nikolai's presentation, they actually started with a completely different subset just to test. So I jumped onto libpq. They started with casting functions for libjson. So if you take a string and you essentially do like : JSON B or JSON, it invokes a function, and that function takes that input that can be from external sources like your web application, so externally controlled, and it will do parsing of that format in C code and spit out the JSON format probably to be written to disk or further processing. So what they did is they started testing that because that's very easy to do a test harness for. There's no state, there's no networking sockets, you can do it very fast, and they found bugs with it very easily. So things are like that are extremely simple to test. Some other things are probably easier for developers to design in the mind of, can we make this component easier to be externally called without having to do a lot of the setup that you saw here? Like the whole harness is like 200 lines of code, and I'm still not sure that I'm doing everything right there, because I'm trying to rip out part of the networking stack and call it and assume that I did it properly.
And this harness that you created is about like one part of the libpq, right? That's
yeah, just essentially for the startup packet and pq get message. And I had to rewrite parts of it to go from pq get message into startup packet.
So you essentially say that everybody who is, let's say, involved in a feature, they should be considered of eventually maybe this will be tested externally and maybe they should create their own harness, or that's how you imagine it?
Yeah, essentially saying like, here's the interface into a fuzzer. Right? So if you have this symbol in your component, like maybe you're contributing a new extension to PostgreSQL, and you have casting functions, and you can do like say, hey, call this to exercise this code path. And maybe you don't have the compute to do this, but maybe then submit your project to something like OSS Fuzz by Google, which accepts open source projects that have this, or maybe somebody like me has time and is bored and sits down and essentially runs a fuzzer for a week on it.
Thank you. I got it. Yes, that's great. Good presentation. Thanks.
Thank you.
Thanks for your talk. You said that there is a possibility to test the whole application, the whole binary build.
Yes.
So in Postgres, we have 20-something small binaries like PG-restore, PG-create-db,
Yes.
blah, blah, blah. Do you think maybe we should start there because they are pretty small so we can cover the area pretty much quickly instead of building the complicated hardware?
That's actually very interesting. I haven't thought about it, especially some of the small tools that do the parsing of like PG control or some or handling rewind, etc. Yep, all of those. Yes, I did look at libpq because I was hoping that if we result with something external, that's pretty big and high impact, right? But probably you're right that I would get much farther, much faster with binaries. So maybe that's another place to start.
Yeah, thanks.
Any other questions? If not, so thank you for our talk.
Thank you.
Very much.